the more we dug into it, the more we realized that it's about cost per bit, cost of service, cost per customer. It all comes back to a business problem.
That is not a very straightforward equation, is it?
No.
Welcome to the OrionX Download. This is a podcast where we discuss and simplify the big ideas in technology that are changing the world. My guest today is Bill Walker, another old colleague from Sun Microsystems who is now Chief Technology Officer for Tensor Networks, an edge computing company. Bill has a pretty unique background, having worked in computing, telecommunications in the US, internationally, and with the technical depth that we look for to discuss important technology trends. Edge computing is important because it combines all of the trends that we track at OrionX. IoT as the fountain of data, 5G as the way data gets transmitted and communicated, HPC and AI as the way we make sense of data, blockchain as an important model for transactions, cryptocurrencies as the way value is assigned and transferred, especially in a world dominated by things, and accelerator technologies that make it all possible within an economic envelope. Edge computing is also important because pretty much all the raw data will originate from outside the cloud, and the vast majority of it will be processed outside the cloud. Let's join the conversation. Bill, thanks for joining us. Exciting topic, fits with a lot of your background in data center and compute and networking and communications and operating systems. So take it away. Maybe we can start by just familiarizing ourselves with your background. Obviously, you and I worked at Sun together, so take us through that if you don't mind.
Oh, absolutely. Thanks for having me, Shaheen. This is Bill Walker. I'm CTO for Tensor Networks. I actually worked at Sun Microsystems 13 years with one little break to go work government research with MITRE, but focusing on kind of the high-end data center and the operational side of things. In about 2010, I was working mostly in the network sector, but from an IT side. And I went over to work in China. I actually worked at Huawei headquarters for about 5 years, working in the CTO office.
I remember that.
Looking at how kind of networks are composed of software. So even if it's a giant black box from Cisco or Juniper, inside there's software that controls the network and controls the packets. When I came back to the US, I went to work for a tier one carrier. I was running an edge group at CenturyLink and looking at SDN and NFV and how we could use the locations of a telco network to actually distribute services. So rather than centralizing and pulling everything back into the cloud, we were looking at why are we paying for all of these giant fiber pipes, and doesn't it make sense to move the data to where it has value?
So that brings us to Edge, and you just mentioned that you ran an Edge group, which I didn't know. So this whole thing is already something that you've been working on quite a bit, and some of it had to do with distribution of services and take them where you need them to be. Let's start with just what is Edge? Edge of what?
Hey, exactly. This was one of the hard problems to explain to people because, edge is it's a buzzword. It's really a marketing word. Edge to me is the edges of data. People think of edge of premise, or telcos think of the edges of their network where their giant router aggregations are and things like that. But what the customers and users care about is data, it's value, it's information. And the idea of edge is to isolate the data where it has the most value or the most savings. So if you're processing large amounts of data, the cloud might be the right answer, or a giant colo location, or rows and rows of processing. But to a site, if you think of a local office, the local office cares about VPN. They care about Zoom. They care about getting their job done, their own email, their own records. So we looked at kind of mixing the whole cloud paradigm of multi-cloud, hybrid cloud back to when we had small and medium businesses that had local processing. And if you look at the data edge of when the data leaves the building, the data is leaving the group of people that care about that data. So if you can process the data local in a fashion where it provides value, then it totally makes sense. So rather than the telco edge of just putting a box in between the telco and your office, maybe we use those boxes at that edge of the premise to process the data within the premise.
I see. So the way you define it, the geographic scope of edge is really a byproduct of
Exactly.
the locality of data.
Exactly. It's a symptom.
So we have this concept at OrionX that we called in situ processing. I don't know if we came up with it or if it existed before, but it was new to us anyway. And it was the idea that data doesn't want to be moved
Yes.
unless it has to. So it really is a question of under what condition does data have to move, and is it worthwhile to move it?
Exactly. And bandwidth is expensive, and as traffic grows, there's a huge expense in burying new cable, in burying new fiber under the ground. And how can we leverage the millions of miles that are already there running at 10 gigabit or 100 gigabit and make them more efficient so that we don't have to bury more cable? And the simple example I always give everybody, and this is called data gravity. If you want to Google something, Google data gravity.
Mm-hmm.
Processing likes to be close to data. If you think of like a surveillance camera at a local gas station, why would I ever send 4 megabits of data streaming from a camera up to Google? The guy who cares about someone shoplifting is the security guy in the store, or the guy at the counter in the store, the police officer who's going to look at the video. What corporate cares about, what the cloud cares about, is maybe how many people are in the store during certain times of day. And that can be done at 1 frame per 5 seconds. 150 times less data than real-time HD streaming.
I see. Excellent. So this leads to, maybe we should go there next, the whole fabric networking part of it.
Sure.
Because you could say that networking keeps getting faster, and as it does, there's a bunch of distance that is being eliminated because of just speed. So to what extent does that change the equation? Maybe it's okay to ship the data elsewhere because you've got the mass quantity of processing and might as well go and come back.
Networks are expensive. I always go back to the burying cables. Telcos have a fixed amount of fiber buried under the ground. And it's great that I can cross the iBone from my house to California by way of New Jersey, by the way, in 30 milliseconds. That doesn't seem like much time. And in web time, in user interface time, that's not much. But if you have an application that's bouncing back and forth to data and referencing data in multiple locations, then the latency adds up. It starts to compound the impact of locality of latency.
I see. So it's still an issue even as networks are getting faster. Of course, the other part is the data size is probably growing faster than the network speed is. That's probably true as well, right?
Absolutely. What does the network double every 18 months as far as data traffic?
Data traffic, that's right. Maybe even faster than that, yeah.
Exactly. But then you look at the cost of moving the data, and the cloud providers generally make more money on the egress of the data into the cloud than they're actually making on the processing in the cloud.
Oh, how interesting.
So you can buy a VM dirt cheap, and your bill for running it for a month is going to be tens or maybe $100. But if you moved a terabyte of data in and out, your data bill is going to be huge.
Interesting. So as you look at this whole now completely decentralized, distributed thing, because we just talked about cloud, we talked about a security camera, so that could be an example of an IoT device or just any device that is connected, whether or not it's smart.
Absolutely.
And we've talked about the circle around the data that basically establishes the edges of data.
Right.
So this promotes the idea of the communication infrastructure, the fabric playing a very central role. So tell us a little bit more about how and to what extent the fabric is becoming the platform.
So that's one of the things that we converged now with Tensor networks. Now that I've learned what we've possibly been doing inefficiently over the last 30 years, let's go back and look at where the data has value. And moving the data in and out of a building really doesn't take much horsepower. So in general, the telcos give a premise equipment box, which is capable of moving traffic and maybe being a slight firewall. But every company has VPN services. Every company's using Zoom. And these are the boundaries of that data between the internet or the public networks and your company, your secret sauce. So in addition to securing the data, what if we process the data? What if we use that to process some data and move metadata, move summaries of data, move some of the data more efficiently and actually cut the bill on the network, but also decrease our usage of the network so that the important data has better throughput and better latency. So we started to look at converging network and computing. When you look at hyperconverged systems today, we have compute and storage and network's kind of an afterthought. So we said, let's start with network and then work backwards to the data. So it's about network and processing and storage when you look at the hyperconverged priorities.
I see. And then in that sense, you have storage. Is it always ephemeral? Is it always just temporary? Is it only cloud for archival?
Some data is important local,
Hmm.
especially if you're talking like a building size or a campus size thing. I see a lot of companies that still keep their HR, legal, and payroll on site, even if they're cloudifying the rest of their business. So some of their critical data stays on site no matter what. Some of the summary data stays on site. And think about even inside a telco network, you're looking at billions and billions of records of telemetry. Think of a telco network as an IoT.
Hmm.
It's an internet of things that are generating lots of data and telemetry. Well, if there's a failure or a cable that's going bad or something which is causing an event, an alert, odds are the guy who's going to fix that or the guy who cares about it is in the same building. So why am I sending data the whole way back to a network operations center so that it can be flagged and dispatch a ticket to the guy in Atlanta who's sitting right beside the problem? So if you look at that and then look at a bank and look at a campus and look at building energy control systems. Look at an oil drilling platform. The guy who's going to fix an oil drill head is sitting there in the oil drill head.
Well, this is a good segue into the TCP/IP stack because some could say, well, didn't layer 4 already do that? You just go straight and bypass intervening steps because you kind of know where it's going to go.
Yeah, exactly. And that's the idea, is that you're routing based on the value of the data or the content of the data rather than just sending everything. When we look at doing local analytics, why not do local analytics of the network traffic? So look at what's streaming. Is the receptionist watching a YouTube cat video? Is somebody on a Zoom call with a customer? You have to kind of be able to recognize what normal traffic is, what the traffic you want to shape,
Mm-hmm.
and then also the outcomes of what you have to work with. So if you're on a 1 gig link and you're really pushing to keep the customer call alive, you probably want to drop the cat video. So we look at AI, ML, and big data around not just the business function itself, but of managing the whole network.
Well, let's talk a little bit about that, although I want to come back to network as well.
Sure.
Obviously, with all this data, you want to make sense of the data, AI, ML, and analytics, probably with some HPC underpinnings. You probably want to do that on the data as you have it because you're also not sending it all back. So you have more compelling reason to do it locally. So, to what extent does that change the equation for how you build these edge devices? Because the traditional view is that these are really low power, both in terms of electricity consumption and in terms of their capability, devices that are just sitting and not doing a whole lot. And now suddenly we're asking them to do deep learning and to solve matrix algebra and signal processing equations.
Exactly.
Yes.
So, one of the things that I did right away is every box that we've designed so far, I can increase the efficiency of encryption and compression by adding GPUs.
Uh huh.
And I don't need many, but they don't come in small packages. I mean, even if you look at a video card, you've got hundreds of GPUs. So I came at this backwards. What else can I use the GPUs for? So I can build an AI ML model. I can build an inference model of what network traffic should look like and start to flag events. So it becomes kind of an adaptive firewall.
Mm-hmm.
But now I've still got 2,000 GPUs in my box. So we started to look at what else you can do with those GPUs.
Uh-huh.
When you're looking at the telcos and their cost optimized premise equipment, so that little gateway box that the carrier gives you for your DSL link or for your fiber, what if that box actually could provide opportunity?
Uh-huh.
So instead of cost optimizing, let's look at what other managed services I could offer on that. Can I analyze your surveillance video for security in a store? Can I listen to the sound of a drill bit on an oil platform to listen for vibration and save a failure?
Oh, I see. So two things. One is that when you say 2000 GPUs, you're talking about 2000 GPU cores, right?
Yes,
Okay, so it's still like one GPU socket.
exactly.
Okay, okay. So now you're fundamentally taking compute to where data is
Exactly.
rather than bring data to where compute is.
Exactly.
And that opens up all the possibilities because then you can do data reduction and learning where you happen to be. What does that do to the programming environment, to the development environment?
That's actually one of the big challenges. When NFV and SDN kind of happened in the telco world, it was more about the vendors taking their software and getting it to run in a VM. I mean, all they did is they took software that was running on a CPU and they made it run on a virtual CPU. And it was pretty easy. It went to market really quick. But it's been really difficult getting any traction on really cloud native, on things that are made to optimize for containers or for microservices. Most of the traditional network vendors have been really slow in getting there. And by having NVIDIA, Intel, other GPUs, and co-processing that is available inside containers, inside the virtualization, it allows us to go faster to a cloud native. And the open source world's actually leading in that,
Yes.
especially with 5G compared to what the traditional network vendors are doing.
Well, 5G magic word, so we now have to talk about it a little bit.
Oops.
Now, on the one hand, you've got SDN and OpenFlow and network function virtualization and all these trends that are trying to simplify how these networks are deployed and provisioned and managed and such. But then you have these new technologies that are coming in. For the wireless one, obviously 5G is the most prominent right now, maybe Wi-Fi 6. But then also at the Ethernet level, you've got other forms like InfiniBand or high-end networking like Cray makes. So there is a spectrum that is being created going from really low power, low bandwidth to really very high-end data center class fabric. So how do you deal with all that heterogeneity when you've got a device out there in the field all the way back to the cloud? Is that expansive view accurate for what the quote unquote platform is?
It is. And we separated that problem into two separate categories. So one is what are my costs to deploy some kind of processing and scale it from an Intel Atom the whole way up, and different classes of GPUs in the different environments. So I have a box that I can bolt onto an antenna. So if you think of a 5G tower with all of the antennas on it, I can mount a box on the tower, or I can put it in a container at the bottom of the tower, which several companies do. But the cost of deployment and the cost of operations of that box are just massively different than traditional data center or a cloud. So you start to look at the volume of data, the cost to deploy, and the latency requirements of the service. You can run an entire 5G network management stack except for one timing function purely in software on an x86 box. Well, now add in the compression, add in encryption, add in a lot of the interesting parts of 5G, and the GPUs start to make sense. That changes the business profile. If you think of a core network, and we talked earlier about a cloud is expensive on network, right? On getting data in and out. So if I'm a telco, would I ever run my core network inside a public cloud? The 5G packet core, where every single internet packet goes through that virtual machine or that software. That means that every single packet from every single cell phone bounces off of Google or Azure or Amazon. I'm double paying. It comes in and it goes out. So it's really a business problem. I mean, you start to balance the cost of fiber versus the cost of the data versus the cost of transport. And then what did you promise the customer?
So really, there's just much smarter ways of accomplishing the task.
Yeah, put the tools where they belong.
Right.
Do you have a kitchen in your office? No. I have one at home because that's where I feed my family. So it's that simple logic that we forgot about 30 years ago.
Well, we were kind of chasing other things.
Yeah, exactly.
Now, is there enough horsepower in these things to actually do the machine learning at the volumes that are coming in? How do you decide whether it's just one GPU socket or two, or whether it needs to be
6.
a little supercomputer up there? Well, now you're kind of getting supercomputer class.
Right. And we look at kind of vertical and horizontal scale on these. And it all gets back to the original architecture of the problem you're trying to solve. One NVIDIA video card, a consumer grade good video card, might be plenty for doing video transcoding and network encryption and compression in a retail store, even a Walmart or a Target or a bigger store. But then if you're talking about doing real video transcoding for college football games where you've got 40 4K HD cameras, that's probably not going to be enough. So we start with a base of, say, I have a high-end laptop sitting here with a NVIDIA RTX 2060. I've got, 2,000 CUDA cores sitting in my laptop. Well, I can now do capacity planning and profiling of the applications I'm developing to decide what it needs in production. And maybe that's a giant 8 GPU socket monster with 128 cores. Or maybe it's a stack of machines with Tesla T4s. It depends how that application is going to spread vertically and horizontally, which gets back to HPC.
Right, exactly. So take us there.
So it comes down to how many nodes do I need? And once you've disaggregated those nodes, you've built yourself a supercomputer. You're looking at the national labs there, scale of things for weather modeling and really interesting things. Why can't that be distributed? So why don't you take your problem and distribute it out as a set of smaller problems, which is which is what the multi-node Linux cluster HPC has been doing for years.
Mm-hmm.
I take the giant problem of solving a hurricane model and I chop that into 1,000 different possibilities and tell everybody to go matrix multiply and come back.
Aha. So now really the question becomes, to what extent do you need all the data in one place to...
Exactly. That kind of distributed versus centralized model, we keep going back and forth. I mean, we had mainframes and then we went client server and then we came back. Now we have cloud.
Mm-hmm.
So, do we decentralize or centralize? And I say yes.
Right, exactly. Right.
I need both.
And of course, when you look at the whole geographically large, like we just talked about, with antenna at one end and devices that the antenna is communicating with, and then all the way back to the cloud and everything in between, if that's the platform, then truly the network has become the computer.
Exactly. This is where it gets interesting, is you start to look at Slurm and some of the tools in HPC for moving work around. And it starts to adapt into this local edge world as well. So if I'm a store, I don't want to be sending all that data back to headquarters, right? I pointed that out. I don't want 20 megabits of constant video traffic. But if there's something important at the store, like it's end of quarter or end of month, and I need to close the books, maybe it's okay to do that for an hour. So being able to distribute the processing when it's normal, and then maybe cut back and do it slightly inefficiently in another time frame for a business purpose, for a value purpose, makes sense. Think of the last episode of Game of Thrones, or a World Series or a Super Bowl game. Your CDN, your video content distribution, is going to be a massive load. Well, maybe it's okay to throttle down Fortnite traffic for a while.
I see. So this gives you more of a dynamic choice to optimize things as necessary at the time.
Right. It should be a business-driven set of decisions. If you think of Netflix, if you're CenturyLink, the last thing you want is a CNN story about how your video service went out during the last episode of Game of Thrones.
That's right.
Or in the fourth quarter of a Super Bowl game.
Well, how do you do that, though? Because you also have promised quality of service to everybody else. But, how much do you have to over-provision to manage that?
Or just provision totally wide.
I see.
So spin up some cloud instances just in case it bursts up higher than you wanted it.
Okay, so there's some maximum capacity you're prepared for, and then within that envelope, you can throttle it back and forth.
Right. Plus 50% has got to be okay, because that means you're successful. And this gets back to the early eBay days and things like that. If you remember, I wrote a book with Adrian Cockcroft on capacity planning.
Yes, I remember.
How can you do capacity planning if you don't know what your peak is?
Right, you can't.
Why are you buying computers against a marketing projection that might be too conservative? So if you're wildly successful, you're going to fail out of business because you couldn't respond.
And we've had examples of that. Yeah, well, capacity planning doesn't seem to go away.
Yeah, exactly.
I remember Adrian posting on Twitter, he was attending a talk, or maybe he was giving a talk. And next thing you know, I'm like seeing Fourier transforms in there. And I'm saying, how did we get that?
Yes.
HPC is like creeping everywhere. And I think that's just because when data gets big enough, that's the only way you can make sense of it.
Exactly. So one of the models I always use is Chevy dealerships, 14,000 plus dealerships in the US, or Walmart, we have 5,000 stores in the US, or even like a UPS with 160 distribution centers. These numbers are off the top of my head. I think they're close. What if, think about it, if you had 4,000 Tesla T4s?
That's not bad.
What could you do with it? If you had 4,000 Intel GPU slots, what kind of processing is that? So you can start to look at, well, what could the corporation as a whole do with this distributed machine? And then what can the store gain value out of that distributed, that local machine, and create business decisions for capacity planning?
Now, a lot of the examples that we've talked about, and of course, maybe that's just because they're nicer examples, there is data flowing relatively constantly, or at least with some level of regularity.
Yes.
Are we always talking about a data streaming model here, or does it not always have to be streaming? And if it is streaming, how does that change your development and deployment strategy, especially because in a decentralized world, you really can't count on service levels from any particular element?
That's what I actually started with. That exact premise that you just mentioned. Is internet traffic sporadic, or is it streams now? And we're moving a lot more towards rich streams. Everything on the internet is more than 1,500 bytes, other than just IoT chatter. I mean, little sensors sending occasional messages. But I started to look at how the traffic actually arrives. And if you think of like layer 2, layer 3, you are getting streams. For most corporate networks, if there's a database server talking to an application server. But then how is that traffic actually profiled? Starting to look at that, we actually decided that Linux and the whole Unix based, and probably Windows too, but I'm not an expert there, how they handle network traffic has always been an exception. So network traffic interrupts the CPU. Oh my God, somebody's trying to log in. Hey, CPU, come handle these packets. And whether it's actual data streams or if it's chatter traffic, the NIC is always busy or the machine is idle.
Uh-huh, uh-huh.
So you're not wasting CPU time by making the assumption that there's network traffic. Well, now profile that even larger, a site or a set of machines or a set of applications, there's always data. And if there's not data, then you don't care because you've got plenty of CPU left over. So we started to look at how Linux and actual operating systems handle network traffic and rethinking how we might rebuild a network stack that could take advantage of co-processing like GPUs and FPGAs, and just spreading that load away from the CPU. The CPU doesn't need to see the packet until it turns into data.
So these are basically what do you call them in a human body? The things that are instinctive?
Right, the autonomic response.
The autonomic response, that's right.
So it's been a great experience actually stepping back and looking at what's the impact. And again, thinking of it from a business perspective, but when your budget is CPU. And going back to the good old HPC days when cycles were expensive and interrupts are expensive and cache lines are your only savior. If you look at the internet as a giant computer and you look at your organization's network as a giant computer, you start to see some real parallels in there of why am I wasting cycles? Why did I just stop a core for 120 nanoseconds because a NIC card said I have a packet? Well, I hope you have a packet. I'm eBay. I'm Netflix.
Could you overdo this though? Could it be the case that now you've got CPUs sitting idle and they actually could be doing some heavy lifting?
God, I hope so.
Because you think you always have stuff to keep them busy.
And that's the idea of AI and of building the inference models is you can refine your models in your spare time. Your upfront model is critical. That's like step one. So get the model there. And then as you start to monitor trends and doing daily and hourly and weekly and seasonal trending on your data, that's not real time.
I see. So you can have batch jobs, basically.
Exactly. Just keep stuff running at a lower priority that refines the model and looks for trends and does the what's normal part so that the CPU is there for exceptions and events and people and business and transactions.
Interesting. I've asked this question that why not consolidate all this processing back on the CPU or back on a batch of CPUs? Because then you're consolidating and you can get better utilization rather than over provision everywhere along the network because you want to do it while it's there. So that optimization problem becomes like how much capacity do I need where for what reason?
Exactly.
And it also depends on actually your fabric speed. So if you are 5G, then maybe you can afford to be even more centralized rather than afford to be even more decentralized.
Exactly.
That is not a very straightforward equation, is it?
No. And think of like GPUs in a machine. So I had an interesting experience last week where someone gave me a very interesting laptop with a big GPU in it.
Uh-huh.
But I have GPU cores in the CPU.
Right.
So it got me thinking about if I could use those GPU cores, if I could use something on die, if I could use something in the CPU to not have to go out to the GPU. All of a sudden, the GPU is my long path.
Yes. You're doing to GPU what it's doing to a network. Interesting.
But that's my long path now. I don't want to use that for a container talking to a container to, decrypt traffic. So the on-die GPU is probably great for encrypting and decrypting disk traffic. So if I have an encrypted disk, that's where I want to do crypto for the disk.
Okay.
But the NVIDIA card sitting out on a piece, and I shouldn't just be saying NVIDIA, but it's an easy keyword.
Right. Well, they become like the Kleenex of GPUs.
Exactly. But, I can have the Intel 5 board sitting out there in my PCI slot that is doing network encryption and decryption before the CPU gets involved. So you start to think of the cost of a GPU and what it would be best utilized for.
So is the answer, unfortunately, it depends?
Yes.
Or are there guidelines? Okay.
I do guidelines.
Rules of thumb,
Rules of thumb. Basically, have the people who do infrastructure and who plan for cloud and who plan for site deployments actually be involved in application architecture, because latency is a key piece of applications these days.
Yeah, very much so.
The guy who's thinking about the latency between a GPU across the PCIe to the CPU is probably the same guy who will understand the difference between Atlanta and Chicago and, Google, Amazon.
Because that's the same math, yes.
Exactly.
Okay, let's get to Tensor Networks. So that's your latest baby.
Yes.
So how's it going so far?
Oh, it's going great. So we've only been in business for about 15 months. We have real customers. We have repeat customers. I still have friendly customers doing my testing and feeding me requirements on the OS. At the moment, I have one bug sitting on my bug list, and it's not a showstopper. So I'm pretty proud of my team. Our CEO is actually a data scientist out of Oak Ridge National Labs.
Nice.
Which is huge. So I've got the 30 years of compute background in IT and manageability, and she's my end user. So she's helping me in driving some of the requirements and helping to build that AI/ML of network traffic. So can a machine learn what it's supposed to do and then adapt? And I think that's actually where we end up. I think that's where Tensor Networks ends up with real differentiation, is the kind of self-aware edge.
I like that, self-aware edge. Tell us, what market gap are you trying to fill with Tensor Networks and how you stack up against other edge devices?
So when we started out, before I came on board, the idea was to create a converged network compute device, the premise edge. And this was responding to what the telcos were doing, trying to build their own or going to the white box vendors to build. And one of the key things that the founders started was putting GPUs in the box. But we sat down and we said, you can't compete with Dell and Lenovo when Intel's giving you a reference design that's 90% of the solution. That's not a good business case. And your software just running Red Hat Ubuntu out of the box is not going to get you anywhere. So we looked at what's wrong with Linux and what's wrong with the way that the telcos are actually doing NFV and SDN and distributing these edge devices. And the more we dug into it, the more we realized that it's about cost per bit, cost of service, cost per customer. It all comes back to a business problem. And if we could accelerate and get in the door by being 10% out of the box faster at the same price as a Dell or Lenovo or Lana or anybody, then that got you in the door. Now, once you're in, you better run that application 20% better in order to get on a procurement list. While we're doing this and fixing the performance things that we saw that were wrong, we also looked at ease of deployment. So we looked at zero-touch provisioning. If I ship a box out to Walmart, there's not going to be an IT guy there. They want to plug it into the network and it magically configures itself and comes up. They also want to plug it into their own OSS, their own management and capacity management and network management tools. So trying to go higher up the stack just made no sense. So what we ended up with was a zero-touch provisioning box that supports all of the standard virtualization types: Linux containers, Docker, Kubernetes, KVM, OpenStack out of the box, pre-configured. But the installer is the magic. It actually crawls through the hardware and says, what am I? And when you install the machine, you don't install 10,000 packages from a menu. You say, this is an AI developer station. Now, I can crawl through the hardware and say, I've got a 10 gigabit NIC, and I've got a GPU, and I've got this kind of CPU. I can make some guesses as to how I should configure the hardware in the kernel and the application stacks for a Python AI/ML developer. So I started to create personalities and then making that repeatable, taking an installed machine with patches and new software that you've added during the development cycle and profiling that and predicting what you need to move into test and production. Remove the development tools, remove the chat client, have a set of rules that decide what a final config should look like. So we ended up being an operating system company that happens to have hardware.
I see, because your hardware is all standard stuff.
Exactly. And the hardware differentiation could be replicated easily.
So the device you're making is on the heftier side of these edge devices. You're going to be serving all these other tiny microcontrollers that are further out.
Yes.
Okay, so that also leaves a bit of a spectrum of these devices. Is it accurate to say that yours would be sort of the culmination of that mini pyramid, so to say?
Right. It's the aggregation of data that doesn't have enough intelligence or enough relationship with its neighbors to do analysis, for the data to have value. Data doesn't have value until it's in context. So at the smallest end, I have a 4-core Xeon D. and I'm running on 8 gig of memory. It goes up to 64, but that box can do 10 gig. So having just a little CPU to aggregate, filter, move things forward, and I've got 192, around 200 CUDA cores in that box.
Right.
So I can do some modeling and some filtering and some compression and maybe even some encryption of the data before I send it on to the next layer.
So depending on the kind of services I wish to offer, I can pick the right configuration.
Exactly. And I said the high end box has 400 gig. The low end box has 4 cores. So
That's quite a spectrum there. Yeah.
yes.
How about environmentals? If I'm sitting on top of an antenna and it's cold at night or hot during the day or smoky like it is now, how do you deal with that? And what does that make you do that you don't have to do in a regulated environment?
So that's actually been one of the fun things is that you get these interesting new challenges. So working in a telco, NEBS compliance is easy. It's not really easy, but it's standard, and standards are easy to engineer for.
It's well understood, yes.
It's well understood. That's a good answer. But someone asks about pole mounting a box or mounting it on the side of a building. That was an interesting problem to me. And you start to think of interesting things like, what if I put solar panels on the outside of the box and use those to power air circulation so that when the sun's up and it's hottest during the day, you're getting free air circulation. Oh, this is great. And we can engineer boxes that run at 130, 140 degree Fahrenheit ambient temperature. This is great. So we started to look at it. And I said, well, what about actual cooling? What if we get into a situation where we actually need cooling? And it turns out I was completely wrong. We needed to add a heater. Because the condensation during the temperature change from night to day, especially in cold weather, means that you'll end up with condensation on the boards and frost.
Oh, wow, yes.
So we actually had to add a 300-watt heater to the enclosure so that we could maintain temperature above the dew point.
And you actually needed an extra heater? You couldn't just use the CPUs faster or the GPUs, throttle them up to generate the heat?
When the box is running, it's fine. The problem that we had is, what if you take the box down?
I see.
Then, you're starting up a box that actually has dew and frost on it.
Right.
There's some interesting challenges.
Extremely.
And we get into NEBs. I've got room temperature boxes that are kind of set-top box, made to be run on a desktop or in a closet somewhere with no air circulation. So the temperature, airflow, these to me are all hobby problems. It's not what I do for a living, but I find them fascinating, and I love to see how the problems get solved.
That is very interesting, yeah. Well, one that probably is not a hobby is security.
Yes.
So, of course, you're now at the edge and you got access to all this valuable data. How do you then go about and deal with the security of it?
Anybody who puts their data on the internet is crazy. So one of the things that we did is we stuck with some of the kind of legacy protocols and legacy architectures of telco. So we support MPLS. We love MPLS. We love private WANs. We love to not have the box actually connected to the internet. If we are, then we're going to do it through a VPN. We're going to do it through an SD-WAN. We're going to leverage everything we can. Now, fortunately, on the Linux side, in the commercial software and open software side, security's been one of the primary use cases for 30 years.
Yes.
So the built-in Linux firewall, I ship with SE Linux turned on and the knob turned up to 10. The only ports open are the ports I know and the ports that I need. And that's becoming a lot more standard in the Linux world these days. And that saves me a lot of effort. So I'm testing what is default most of the time.
Right. So SE Linux is the security enhanced Linux. Do I have that right?
Yeah. So SE Linux came out of the National Security Agency, the NSA in the US.
Okay. They would know a thing or two.
Yeah, it's a profile of shutting down ports and not leaving things open and not doing things stupid. But SE Linux also has a permissive mode. So if you're doing development and you want to have the ability to open a port or install a package, it will warn you if you're doing something against policy or if you're doing something stupid, which is awesome. Because then your young developers fresh out of college learn why that might be a bad idea.
That's really not a bad idea, exactly. So excellent. What have I not asked you as a edge device, AI, ML, HPC, 5G? We've touched on a lot of different things.
So one of the biggest problems we have is use cases. And this gets back to being an adaptable small company. This is why I actually have faith that we'll succeed even up against the Ciscos and the Dells and the HPEs. If we knew about the iPhone in 2003, we'd be rich, right?
That's right.
If AT&T had known about the iPhone before 2006, New York City would not have gone dark for mobile internet. So it's interesting that the use cases and the problems that we're not seeing, that we haven't predicted, and the legacy thinking like this is 1990 or even 2009 and cloud is the greatest thing, means that we aren't open to the new architectures and the new ideas. And I really think that if you look at Fitbit had a great opportunity, but they engineered for the cost of acquisition, the cost per customer, the cost per device. So they have consistently shipped a $100 fitness device that has some new features and has an app for your iPhone, and it's pretty cool. But then you look at Peloton and you look at how people say a Peloton bike is too expensive. Great, let's license the software to Roku. Let's put it on every TV set for $12 a month. So I'm not going to sell you a $2,500 bike, but I'll still get you $12 a month. So having that kind of market adaptability and that kind of thinking forward, what else could I use this for? What else could my customers be doing? And why are we doing it that way? Well, it's how we do it. That's not the right answer. So I think that's where I actually see the opportunity is building a platform, being ready for the next challenge. 4K TVs. If somebody figures out how to make a 4K TV $50, the networks are going to die.
Right.
Now you talk to the telcos. Am I going to transcode the video live at a metro level and not give everybody a 4K stream if it's going to kill emergency calling on the telco network? Okay.
Right, exactly. Yeah. Well, I think that's a wonderful thought to end with, and that is, let's try to imagine what 2030 looks like.
Right.
And I think we are in the cusp of so many different changes technologically that impact every aspect of life, that sort of thinking is not just a good idea, it's a requirement.
It is for success. I mean, you remember when you got your first meg at home and you didn't have to use a dial-up modem?
I do, yes.
Oh my God, you could never use that much bandwidth. And now, I'm using 4 times that to stream a movie.
I know, that's right. In fact, I was just telling a friend that I couldn't believe how fast it was.
Yeah. Exactly. So, I mean, what happens next? No matter what you give people for technology, they'll push you for an extra 20%.
That's right. Well, excellent. Bill, thank you so much. I wish you all the success with Tensor Networks. Please keep in touch. And obviously, this whole edge computing area is just beginning, and you're on the leading edge of it. So there will be a lot more developments to come to you and catch up with. So thanks for that.
Sounds great. Thanks for having me, Sheen. I appreciate it.
All right. Perfect. Big thanks to Bill Walker for spending time with me today to help unpack various aspects of edge computing and give us an update on Tensor Networks. I look forward to catching up with him again in the future. And thank you for listening. Until next time, take care and study hard.